Hey guys, welcome back to VT GeoChat, the official podcast of the Department of Geosciences at Virginia Tech. I'm your host, Rose McGroarty. It is so great to be back with you again this week. And today I am joined with Dr. Mateo Acosta. He is a new faculty at Virginia Tech Geosciences. We're so excited to have him. And we're going to be talking about his paper, Flow to Quake, an integrated multi-phase flow geomechanical and seismicity model for efficient forecasting of injection and extraction induced earthquakes. I'm excited for this, but before we get into it, please make sure to like this video, subscribe to our channel if you have not already, and guys, we have been through so many of these podcasts by now. Please, if you have not followed our page, please subscribe, and also make sure you ring that little notification bell because you want to make sure that you get all of our uploads as soon as we upload them. So, Mateo, I'm going to turn it over to you. Tell me about your paper.
Thank you. Thank you for having me, Rose. So the paper, it's the end of a few years of work, both of myself and some students of mine. And the idea is that we developed this modeling workflow that allows us to understand induced seismicity due to fluid injection or extraction in the subsurface.
And sorry, can I cut you in for a minute? Induced seismicity, you mean earthquakes that are man-made,
exactly.
Right? Alrighty.
Exactly. And so the idea is that, there's a bunch of different types of operations that could get us to a decarbonized economy, such as sequestering carbon underground, geothermal energy exploitation, hydrogen storage, things like that. And the common ground of all these activities is that they all need either to inject or extract some type of fluid in and from the subsurface. And as you're injecting and extracting, you're changing the pore pressures, you're changing the stresses in the subsurface, and you can reactivate faults and generate earthquakes. And we want to understand those and forecast them for a given injection or extraction scenario so that we can better manage them.
And how bad are the earthquakes that they generally generate? Are they severe? Are we talking about flattened buildings? Would people notice them, or do we not know that yet?
That's a really good question. So they're, in general, not that big. You wouldn't expect magnitude 7, magnitude 8 earthquakes due to these operations, although there have been cases where a magnitude 7 earthquake has been recorded. The attribution to the fluid injection and extraction operations is not so clear for those very large earthquakes, and we think that those very large earthquakes are mostly happening in faults that were ready to go, and then we just kick them with our operations. Yeah. In general, they stay small.
But still, we don't want them. We still want to understand that, yeah.
Yeah, exactly. Exactly. And we want to understand, which faults are ready to go and so on. But that's the idea. And so this paper developed a method for a bunch of different reservoirs that are very common in these operations to use the minimum physics possible and have very efficient modeling workflow to simulate these activities and to get down to the mitigation of the induced earthquakes.
Okay.
Yeah.
So can you tell me about how did you do that? I'd love to hear about your methods.
Yeah, so the idea is that we decompose the very complicated physical process from when you're starting to change the fluid content at a borehole, all the way down to the seismicity. We decompose that into a few different modules. So we have one module that simulates the fluid flow in the subsurface, another one that simulates the geomechanical deformation. So you can imagine it like a sponge. So if you're pushing fluids into a sponge, it will dilate, right? And it will, as it dilates, it will push on the sides of whatever is holding it underground, and then that push will change the stresses and can generate that seismicity that we want to understand. And so we decompose these things, we stripped out all the complicated physics to the minimum, and we came out with this very efficient workflow for managing the seismicity.
Okay. So this is a computer model or a...
Yes, correct.
Okay.
Correct. So this is a set of computer models that work together to get us all the way through that process.
That's pretty awesome.
And so the very interesting thing about our approach is that it's a very much data-driven approach in the sense that we strip out the physics in the models and so on, and then the few parameters that we still need to calibrate, we calibrate them with real data on real fields, on real operations, and so the models are very robust for the later forecasting because they have been calibrated on real data.
So did you go out to the field to collect the data, or did you get data that was already published in the literature?
We mostly got data either that was published in literature or that some industrial partners shared with us, and so on. It was a huge amount of the work was to curate that data and to have it in the nice formattings for our codes to our models to absorb that and get it going through that workflow.
Oh, cool. So what can you tell me about your results? What's the big takeaway from this paper in terms of results, or what did you get from it?
So I think one of so there's a few results. One of them is that we are getting really good at forecasting the seismicity nowadays. So if we have enough calibration data, we can give you a very good forecast that matches whatever we're seeing in real time. And so that has been proven for several operations, some of gas extraction, some of gas injection in the subsurface, and we're actually getting really, really good at it. The other, which I would think it's a more subtle but extremely important result, is that we are able to quantify the uncertainty on the forecast, and like how certain are we that we expect this many earthquakes in a given year or in a given month, right? Not many codes can do that because of the numerical cost of it. Usually these fully coupled models are very expensive, and so you cannot run hundreds and thousands of simulations because of the numerical expense. And since we strip down the physics to a minimum that still reproduce the observations, we are now able to quantify how certain we are, which is huge. Yeah.
So I'm going to back up. I'm going to ask you a question about your methods. Can you explain, you keep saying that you strip down the physics. What does that mean to strip down physics? Kind of like in a nutshell, very broad.
Yes, so broad is that, when you're thinking of earthquake physics and how you get to, inducing an earthquake, there's a lot of processes that come to mind. There's, fluid pressures acting on the stresses and acting on the fluid diffusion, maybe thermal stresses and thermal problems as you're injecting cold fluids into the subsurface. You have multi-phase flow physics. You have a bunch of different things. You also have the physics of earthquake nucleation, which are very complicated and we don't grasp them really well yet. And what we did is to understand really well our geological systems, understand really well our reservoirs where we are doing these operations, and take out as much as we can without compromising, the actual process. And so we took the minimum physics that are needed to explain the observations, coupled them together in this train of work, and allowed this very efficient modeling.
Okay, nice. So you basically just you took what you needed to explain, but you didn't keep the extra complications, the factors of then there's this factor impacting this other factor impacting. You only focus on what physics you need to describe this particular mechanism.
Right.
Gotcha.
Exactly.
Okay. And so it sounds as if this is a pretty novel approach. You said that this actually makes it easier to understand and more accurate. I am curious, could you tell me what do you think of this paper is the strongest point of the paper? And it could be, maybe it's a novel approach, novel contribution, or maybe it's something where maybe it's just a particular method that you did that you feel particularly strong compared to what other people are doing. What about this paper really stands out and makes you say, okay, this will contribute to our science?
Yeah, I would say the best thing about this is its simplicity, in a sense. As I told you, we stripped down the physics to the bare minimum, and so it makes it that, within the difficulty of understanding it, it's still one of the simplest physical models that allows us to explain the observations. And to me, that simplicity is the beauty of it, because that simplicity allows us to quantify how certain we are, right? And to do this really efficiently for new operations and for other types of settings, in a really fast and efficient way, so that we can provide a tool to the industry to actually, manage their operations in a much more informed way. So I would say it's simplicity.
Okay.
Yeah.
Now, and we all know the acronym "Keep It Simple." So that
Right.
I guess it's always fun to me to see like all this really complicated. I mean, I'm sitting there thinking, "Wow, this just sounds so complicated." And you're saying, "Oh no, it's actually very simple."
Yeah, well, it's actually very simple with respect to what it could be and to
Right.
what the standard is nowadays. The state of the art is. We are working a way simpler domain, way less parameters to calibrate, way less complications, I would say.
That's cool.
It's interesting.
Yeah. So less fun to ask about, less fun to talk about, but it is, a part of science is being open and transparent about this sort of thing. So that's, something that I like to ask people. So can you tell me, what do you think is the weakest part of the study, or what could have gone better, either in your data, in your modeling, in your maybe ability to compute as many models as you want, anything that you just think could have been better and would have made this study stronger?
Yeah. So there's one limitation is that because of the striping down the physics to a bare minimum, it cannot be applied to any operation in the subsurface. And so there's cases where our workflow will not work because the physics don't go with those type of situations. But it can be applied to a bunch of them, to a bunch of similar reservoirs, which we are targeting for carbon capture and storage, for hydrogen storage, for conventional geothermal operations, and so on. And so I would say that's the biggest limitation. And the other one is that, of course, because of the data curation process, which is very time consuming and so on, we couldn't apply it to tens or hundreds of cases, but we restricted ourselves to a few.
Right.
And so that would be the other limitation.
So it sounds like being able to apply it to more cases, or also maybe expanding the model in some way to apply to more different situations would be some ways that. Oh, okay.
Yeah, exactly, and that's what we're working on here at Virginia Tech with
perfect.
my students. So I have two students that are working on this, Rahi and Lily, and they will use different parts of this modeling workflow to apply it to different cases and to expand on this and to get better at it, and
nice.
to also to understand what's our limit until where can we push this.
And that pretty much answered my next question, which is what are the logical next steps for this? So so you're just continuing on this same trend. And
so there's part of continuing to understand different systems that we're working on, but this opens up the possibility of very novel and very important things. So, for example, one of them is something my student Rahi is working on, and is putting a feedback loop into the modeling workflow so that we can control in real time the seismicity.
Cool.
And we actually just published on some other case with another student of mine a paper where we demonstrated that this is feasible. And so now the idea is, okay, let's combine the two parts of it, the efficient modeling with this feedback loop, so that we can propose a tool for the industry to actually regulate their induced seismicity in their operations. So that's one thing. And the other thing is to think about novel ways of characterizing the subsurface using this modeling workflow. And so we want to understand how the heterogeneity in the subsurface reservoirs affects, for example, the establishment of a very large carbon capture hub, where you have many different projects interacting with one another, and we need to understand who's causing which earthquakes and so on. And so that's a big part of what we're doing with Lily.
Oh, cool.
My other student.
Oh, that sounds awesome.
Yeah.
And this, I know geothermal, any type of renewable, green energy is very big right now in terms of research and people just interested in studying it. So that also kind of leads me to ask, and I know that this is a way I've answered my own question because I just said it's a very big field, but what opportunities do you see for future students? So either college students who are interested in graduate studies, or maybe we've got some high schoolers who are starting to look at majors and starting to think about what they want to do, and maybe they've been really interested in this. What opportunities do you think there are for up and coming professionals?
Yeah, so that's a really good question, and it's difficult to pinpoint a few because there is so many of these, but we have worked on this, myself and my collaborators, in a way that it's all the numerical part of it, the codes are very easy to use, and I have come up with training videos and very good documentation about the whole modeling workflow, so that I can train you in probably a week. If you're familiar with Python, in a week I can have you up and running simulations of fluid flow, geomechanical deformation, and seismicity at the end of it. And so for anyone that wants to do an internship with us or wants to start undergrad research with us or whatever, it's very streamlined to have you working with us in a really quick way, and that could open a lot of doors for positions in the industry where you need to understand all these processes that lead to induced seismicity, which have halted unfortunately a bunch of these subsurface operation projects.
Oh, that's awesome. And the fact that you're using Python is great too. And I'm just going to say as a shout out to anyone watching this that Python is free. So you can learn how to use Python yourself if you want to get a kind of a head start on this kind of research, and be familiar with that type of coding, so that you can come and do type research like this using Python. So that's great that you mentioned Python. I think those are pretty much all the questions that I have for you about the paper. I do just want to add quickly for our viewers that Mateo, this is your first semester, I believe.
Second.
So your second semester, so you came last. Okay. I know you have a new office. Yes. But Mateo's lab is opening right across the hall from our recording studio, actually. So please stay tuned, because we're going to do a tour of the lab and show you the equipment that he's using for this modeling work. And I'm very excited about that. I've seen it being brought in and installed. It looks fantastic, so exciting. So I'm really excited for that once you have it up. So please stay tuned for that, because we will be sharing little tours of the lab, and that's going to be a lot of fun.
Yeah, and actually, so that's just a quick, clarification there. What we do in my laboratory, that's called Earth Mechanics and Physics for Energy Sustainability. We do this modeling and observational side of the research. That is what we've been discussed about this paper. But we do also perform experiments on real rock samples. We submit them to high stresses, very representative of those subsurface reservoirs and so on, and then we study the physics of it in the lab with this big equipment that Rose was telling us about.
Well, I'm looking forward to being able to see all this in motion and show it to people. So
definitely.
I was excited to see it. I'm really looking forward to that.
It's gonna be awesome. We should be up and running by the end of the month. So
that'll be so much fun.
It's gonna be great.
We can all keep an eye out for new stuff coming out of your lab too.
Excellent.
We're all excited for it. So thank you so much for being on the show today. It's been absolutely wonderful having you. Hopefully we'll have you again as more papers are coming out of your lab. It'd be great. I'm looking forward to that tour. So everybody, please keep an eye out on our social media pages, on our YouTube and our Instagram and Facebook, because we will be posting that tour of the lab. I'm very excited about that. And in the meantime, please let us know in the comments what you think. If you have any questions, I always love to hear from our followers on any of our platforms. So it makes me feel a little less like I'm talking to the void to get some comments and feedback and questions from you guys. And I'm happy to relay questions if you guys have questions for Mateo. The paper will be posted in the description of this video, as well as maybe any other papers that you want to send along. I can post them in the description so that you guys can see this research for yourself. And so, stay tuned for our next episode next week. I feel like I've got a lot of announcements this week. The lab tour, next episode next week. Just a lot going on. But thanks guys so much for listening. It's been great having you here today on the show. It's been great having you here as our audience to talk to. And as always, guys, stay lava.